Okay, let's talk about voltage divider bias. And what that is, that's if you have a circuit that looks like this. Let's say we have a source of 10 volts here. We have 3.6 kilo ohms here. We have our transistor here. We'll give it beta equals 100. We have an emitter resistor of 1K. But now this end is not being attached to ground. It's actually attached right here to a resistor here of 10K and a resistor here of, let's say, 2.2K. This circuit is really equivalent to drawing it this way. So redraw the circuit. This is the 1K, that's the beta equals 100. And now, here's my resistor, the 2.2K. Here's my 10K on the top right there. And you have a voltage source here of 10 volts. These two are the same. Now the correct way to do this problem is to find the Thevenin equivalent of this one. Because if you know what the Thevenin equivalent of that, then you can take that circuit and replace it with this. And again, beta equals 100. And I'm going to replace this with R Thevenin and V Thevenin here. And the question, how do we find what V Thevenin is? And how do we find what R Thevenin is? So let's take that circuit and replace it with these two, with V Thevenin and R Thevenin. If you remember from circuit, maybe, I don't know, last semester, the semester before, circuit 1, if you have a circuit like this, and you try to find the equivalent of that, the Thevenin equivalent, so let's say I want to find V Thevenin first. V Thevenin is really V open circuit. So if you cut the circuit right open here, what's the voltage right there? That's what V open circuit is. And that happens to be a voltage divider. You take this source, which is 10, you multiply it by 2.2K over the sum of them. Again, if you remember, that's called voltage divider or voltage division. And if you do the math, approximately this is 1.8 volts. So that's my V Thevenin. Now what's R Thevenin? R Thevenin, that's when you take the circuit and you replace every voltage source with what? With the short circuit. And every current source with what? With an open circuit. Short circuit here. And R Thevenin is R equivalent looking that way. That's what R Thevenin is. If you were to look back that way, what is the R equivalent of these two? Well, these two resistors are connected in parallel. So R Thevenin for two resistors in parallel, we call that the product over the sum. So R Thevenin is going to be 2.2K times 10K over the sum of them And now that gives me a value of 1.8 kilo ohm. Wow, it's the same number. 1.8, 1.8. Is it always the case? No. So why is it the same this time? Well, I'll give you the answer. Notice this voltage is what? 10, and what's that resistor? 10. That's why. If you change one of these two numbers will not match. So now we're going to take our circuit from here. This is the one. I'm going to replace Thevenin with 1.8 volt. Replace that with a value of 1.8 K and solve it. $3.6K. $1K. Now here's my R Thevenin, 1.8K. And here's my V Thevenin now, put it right there. And that's 1.8 volts. Beta equals 100. So if I do KVL right here, sum of the voltage in a closed loop should be 0. That's what KVL is. The one thing you have to remember that the current going through this resistor is not the same current going through that. This is I sub B, but the current through this one is I sub E. Going back to circuits again, transistors, we know I sub E equals I sub C plus I sub B. And I sub C happens to be beta times I sub B if you are in active mode. So when you add them, what do you have? 1 plus beta times I sub B. That's what I sub E is equal to. So in this example, beta is 100, or HFE is 100. So I sub E is equal to 101 times I sub B. Now let's do KVL right here, Kirchhoff voltage law, which state what? Sum of the voltage in a closed loop should always be 0. If you add all the voltages in a closed loop, that sum is always a 0. And it really doesn't matter if you label minus to plus as a minus and plus to minus as plus, or minus to plus as a plus and this is minus. As long as you're consistent, your answer is not going to change. So I'm going to do mine as minus to plus as a minus. So minus 1.8 plus the voltage drop here. The current is going to the right, it's going to mark it plus to minus. And that's 1.8 K, that's the resistor, times the current, that's Ohm's law. V equals I times R. We know what I, we know what R. Add to it the 0.7. Let's take the voltage drop here. Again, Ohm's law, V equals I times R. I is what? I sub E, and R is 1K. All of that should equal to 0. I don't know where the 7 came from. What's 1.8? Negative 1.8 plus 0.7, that's negative 1.1. If I move it to the right side, that is 1.1. And here I will have 1.8K I sub B plus, in place of I sub E, I'm going to put 101 I sub B times 1K. $102.8K I sub B is equal to 1.1. What is I sub B equal to? 1.1 over 102.8, which is what? That's approximately 10.7 microamp. So 10.7 microamp. If we know that, now we know it, not if, now we know it, can we figure out what I sub C is? It's beta times I sub B. Multiply that by 100, that's 1.07 milliamp. And what's I sub B is going to equal to? It's I sub C plus I sub B. So if you add these two numbers, guess what you're going to have? You're going to have 1.08 milliamp. Let's take a peek here that we know all these things. So let me just write I sub B here on the top so I can leave my paper sitting there, which is 10.7 microamp. Can we figure out what the voltage between C and E? Right here we'll call this E, and this is C. Well, VC, the voltage at C, is going to equal to what? The 10 volts on the top minus the drop right here. Remember, there's I sub C coming through this. So it's going to be minus 3.6K I sub C. There's the calculator again. 10 minus 3.6 times I sub C, which is 1.07. And roughly that's 6.15 volts. And what's VE, the voltage at E? Well, this end is ground here, so it's only the voltage across that resistor, which is what? I sub E times 1K. And I sub E was 1.08, so 1K times 1.08 milli, and that's 1.08 volts. Do we know what VCE now? VCE is actually VC minus VE, which is 6.15 minus 1.08, and if my math is good, that's 5.07 volts. Let's double check that. .07 volts. Notice there was a lot of math, a lot of work in that. The other thing I want you to notice how small I sub B is in the microamps. So guess what? If you're a technician on the field, you want to check to make sure that transistor is working or not. You don't want to do all this math. So what's the other way of doing it? Well, the other way is to neglect. You notice how we calculate V Thevenin to be what? 1.8 volts? Just use that without even using that resistor. Just don't even bother with that resistor. Drop it. So let's see. I'm going to redo the problem without dealing with this resistor by dropping this resistor completely and see if that will change my answer. And if it does, make my math easier. Here's the problem. 10. That's 3.6K. $1K. And I'm going to drop that resistor out and just put the 1.8 volt here. And this is beta equals 100. Same problem. I'm just neglecting that resistor. Well, I know this voltage here has to be 0.7. So that tells me the voltage here is actually 1.1 volt. Then I know what I sub E is. So I sub E is going to be what? 1.1 volt divided by 1K, which is 1.1 milliamp. Notice it's an approximation. Let's compare it to the true value. What was my number, the true value? Let me see, where did it go? My true value, when I did the math the long way, it took me 2 pages to do it, my answer was 1.08. So if you round that to 1 decimal place, it's 1.1. Not much of a difference. Let's see if VCE is going to change by a lot. Again, since this current is really small, you can make the assumption that I sub C is approximately I sub E, which is equal to what? 1.1 milliamp. So what's the voltage at C here? VC equals what? 10 minus 3.6K times I sub C, which is, I said, approximately I sub E. And I got 6.04 volts. And what's VCE? It's VC minus VE. VC is 6.04 minus VE, which is 1.1. And what do we have? .9 volts. That's a quick approximation without having to do a lot of work. If you want to get closer to that, you can actually figure out what I sub C is instead of using approximately 1.1. How do we figure out what I sub C is? We know I sub E equals I sub B plus I sub C, and I sub B or I sub C equals what? Beta I sub B. So if you really want to do that, you can replace I sub B with what? I sub C over beta. So I sub C, that's 1 plus 1 over beta. So in this example, beta is 100, so it's 1.01 I sub C equals I sub E. And if you want to find what I sub C is, divide actually that current I sub E, which is the 1.1, by that number. We're talking about 0.1 volt or 2 milliamps, not 2 milliamps, 0.02 milliamps, like 20 microamps or 5 microamps, minor values. You end up with I sub C here equals 1.09 instead of 1.1. So if you do the math, 1.09 here, you end up with 5 and some change here. But again, when you're working on the field, you're trying to get a quick idea what the value is. Is that transistor working? These are the quick approximation we use. We're going to neglect that resistor. The current going through it's very small. It's not worth mentioning. Do it this way, find I sub E. I sub B and I sub C are going to be very close. Notice I sub B is 1.1, I sub 0 is 1.09. If you round that to one decimal place, that's 1.1. So it's almost the same number. So many people actually will do these problems using this approximation method. And I'll stop here for this video.